Hello and welcome to This Explainer. Okay, today we are going on a seriously mind-bending journey that's going to completely reshape how you look at the night sky. We're going to contrast our own cosmic backyard, our solar system, with the vast, uncharted real estate of the rest of the Milky Way galaxy. For centuries we've looked up at the planets orbiting our sun and just kind of assumed they represented the standard blueprint for the whole universe. But thanks to some wild recent astronomical discoveries, we're finally meeting our cosmic neighbors. And frankly, they are absolutely nothing like us. So here is the fundamental question I really want you to keep in the back of your mind as we go through this explainer. Is our solar system actually normal? I mean, it's a simple question, right? But it completely challenges our assumptions about humanity's place in the universe. We all grew up learning about our specific set of planets, but when we actually look out into the dark, are we the rule or are we the exception? Let's find out. Okay, let's dive right into this with Section 1. Our structured solar system, the familiar baseline. As you probably know, our solar system features a very neat, tidy division. Right up top, closest to the sun, we have the inner terrestrial planets, Mercury, Venus, Earth, and Mars. These are incredibly dense, rocky worlds made of refractory minerals and metals, stuff like iron and nickel. But as soon as you move outward, the architecture completely changes. We hit the massive outer Jovian planets, Jupiter, Saturn, Uranus, and Neptune. These are massive giants composed almost entirely of gases and ices, built from elements with super low melting points like hydrogen and helium. It's an incredibly organized system. But why is it split so perfectly like that? Well, the answer comes down to what astronomers call the frost line. Early in our solar system's history, the intense heat and light pressure from the young sun basically pushed all the lighter, volatile gases far out into space, while the heavier, rocky materials with high melting points stayed close. Right around 5 astronomical units away from the sun, which, to put that into perspective, is exactly 5 times the distance between the Earth and the sun, the temperature drops just enough for those volatile substances to finally freeze and coalesce into ice. That invisible boundary literally acted like a cosmic sorting mechanism, structuring our solar system perfectly into 2 distinct halves: rocky worlds on the inside, giant gas and ice worlds on the outside. It's elegant, right? It makes total sense. Now that brings us to Section 2. Finding worlds through wobbles, expanding our horizon. How do astronomers even know what these distant, hidden exoplanetary systems actually look like? To find these distant worlds, we have to look at gravity, specifically a concept called the barycenter. Now, as a quick refresher, planets don't actually orbit the exact dead center of a star. Actually, scratch that. They orbit a common center of mass. Think of it like a shared balancing point on a seesaw. Jupiter, for example, is so massively heavy that the shared barycenter between it and the sun actually sits just outside the sun's surface. So, in a very real way, the sun is literally being tugged around by its own planets. So let's walk through exactly how this helps us find exoplanets. Step 1. Even though a star is humongous, its planets still exert their own gravitational pull right back on it. Step 2. As the planet moves through its orbit, the star is pulled slightly off-center to orbit that shared barycenter we were just talking about. And Step 3. Because the star is orbiting this slightly off-center point, it actually appears to physically wobble back and forth from the perspective of us observers here on Earth. Detecting that tiny, rhythmic stellar wobble is absolutely crucial. It's the brilliant key astronomers use to find hidden exoplanets orbiting completely distant stars. All right, moving on to Section 3, contrasting planetary sizes, the missing pieces. Let's take a look at a really specific number here, 318. This is a pretty awe-inspiring data drop. Jupiter has 318 times the mass of Earth. I mean, just think about that huge gap for a second. We have Earth, which is the absolute largest of the rocky planets, and then the very next step up in our solar system's hierarchy is a massive gas giant 318 times heavier. And this brilliantly illustrates why our own system might be, well, kinda odd. In our solar system, we have this massive, gaping-sized void between Earth-sized rocky worlds and those massive Jovian gas giants. There is literally nothing in between. But when we look at extrasolar systems, we find a wild abundance of what we call super-Earths, planets that are larger than Earth but smaller than Neptune. They are absolutely everywhere out in the galaxy, filling up that exact size gap perfectly. Yet in our own solar system, this incredibly common type of planet is just completely missing. Weird, right? That brings us to what might be the most bizarre contrast of all. Section 4, the dance of orbital resonance, mathematical perfection. The phenomenon at play here is called orbital resonance. To really understand it, consider this quote. The physical principle behind orbital resonance is similar in concept to pushing a child on a swing. When orbiting bodies exert regular, periodic gravitational influence on each other, it's exactly like giving that rhythmic push on a swing. Because their orbital periods are related by a ratio of small integers, they give each other a cumulative, rhythmic gravitational push. This creates an incredible, mathematically precise cosmic dance. Now, we do have a little bit of this in our own system, like between Neptune and Pluto, or even some of Jupiter's moons. But what we're seeing out in the wider galaxy takes this idea to a completely different level. Now, what's really interesting about these findings is the sheer mind-boggling complexity of these multi-planet chains. Take the Kepler 223 system, for instance. It has 4 different planets locked in an 8643 resonance. That means while the outermost planet orbits exactly 3 times, the next one orbits 4 times, the next one 6, and the innermost one completes exactly 8 orbits. It's like a flawless cosmic clock. Or, no way, look at TOI 178. It has 5 outer planets locked in an 189643 resonant chain. It's just perfectly timed. And then there is the TRAPPIST-1 system, which is just an absolute marvel of nature. It features 7 roughly Earth-sized planets, packed incredibly tightly together in the longest known chain of near resonances. It is so perfectly and rhythmically structured that scientists have literally provided a musical interpretation of its orbital frequencies. Just imagine that for a second. An entire solar system acting as a synchronized, self-correcting musical instrument out in the void. So you might be wondering, how do systems even get this packed in the first place? Well, take the Kepler 90 system. It has 8 known planets, just like ours does, but it has a series of tightly packed inner super-Earths. The math actually suggests that the presence of a massive outer gas giant facilitates this whole setup. As the system forms, those massive outer planets act like gravitational bulldozers, helping to push and sculpt the inner planets into these bizarre, closely packed, resonant configurations. Which leads us to our final point. Section 5, Are We the Outliers? Reevaluating our place. Let's summarize the core contrast here. Our solar system features wide, spacious, and largely independent orbits, with absolutely vast distances between our planets. Plus, we have that completely empty gap where super-Earths should be. But in stark contrast, the extrasolar systems we're finding out there are characterized by tightly packed, mathematically locked resonant chains. Their planets sit incredibly close to their host star and to each other, locked in a perfect gravitational rhythm. So that leaves us with this final, really provocative thought. Does our lack of tightly packed resonant chains make us the weird ones in the galaxy? Are our quiet, incredibly spacious orbits actually the ultimate anomaly? The more we learn about our cosmic neighbors, the more it seems our so-called normal solar system might just be one of the strangest pieces of real estate in the entire Milky Way. Thank you so much for joining me on this explainer. Keep looking up because the universe is far stranger and far more rhythmic than we ever could have imagined.